Number 19, I am asked to find how much a function will change between one point and another point not too far away. The book is a little bit weird on this because the book presents the method to find linearizations before it presents the method to find total differentials and these well this estimating error kind of thing. And so it seems to me that the exercises in the text are a bit out of order. So I would not have done things this way if I were writing the text, but I would have done some exercises involving linearization first. But at any rate, the total differential of a function, and I wrote down the function that the textbook has here for 19, but actually for any function, the total differential df is df dx dx. So think about it. These would sort of cancel the dx and the dx. That's how Leibniz would have thought of it, though he was a little bit off because the algebra doesn't quite work out, right? You wouldn't have df plus df plus df. No, the idea is you have one term here for each variable. Think about it like this. The change in f is the slope in the x direction times the movement in the x direction plus the slope in the y direction times the movement in the y direction, and the slope in the z direction times the movement in the z direction. Now you can't really call this slope because we have three variables, but the rate of change, how much does f change when z changes a little bit, times a little bit of change in z is the idea. Now, that can be split apart into a dot product. The gradient of f, of course, the components of gradient of f are df dx, df dy, df dz, and this vector dx, dy, dz. The idea is this is a vector with very small, infinitesimally small components. And so we can measure how quickly f changes when you, or rather, how much f changes when you move from one point to another point, dx, dy, dz, away from it. So maybe in blue just over here, I'll say, f has a value at some point over here and a value at this point over here. And if you have some vector like this whose components are dx, dy, dz, and you want to know how much the function changes, df, between here and here, well, this is an expression that actually gives an approximation of it. Right? This is only an exact equation when these really are infinitesimally small, which doesn't really mean anything. It's more of an emotional plea. Think that this is actually an approximation. It's only an equality, emotionally speaking, when these differentials are actually infinitesimally small. So anyway, let's calculate this thing. The reason this is in the section is we're learning to deal with a gradient, right? Okay, so the gradient of f, let's see, the derivative with respect to x of that expression is x over x squared plus y squared plus z squared. Okay, and derivative with respect to y is similarly y over x squared plus y squared plus z squared. Gosh, I should have factored out the x squared plus y squared plus z squared. Oh well. Z over x squared plus y squared plus z squared, and still have to dot with dx, dy, dz. And so now the idea is this gradient is a different vector at every different point in three-dimensional space, the domain of this function. So what I should do here is I should be thinking about where I am meant to evaluate the gradient. So the question in the book, by about how much will this function change moving from 3, 4, 12. Let's now, the total differential of the function, maybe I'll add in right here, at 3, 4, 12. Is df evaluated at 3, 4, 12? Sorry, that came out a little bit too small right there. You might not be able to see it. And then all this evaluated at 3, 4, 12. Okay, and so I need to evaluate this at 3, 4, 12. And that means I need to evaluate this at 3, 4, 12. Oh boy, something tells me 3 squared plus 4 squared plus 12 squared. Okay, 3 squared plus 4 squared is 25. 25 plus 144 is 169. 116. That's 13 squared. Oh man. Okay, so this is so the denominators of all of these are 13 squared, or 169. 13 squared. And the numerators are 3, 4, 13 squared, and 12. Okay, and that I dot with dx, dy, dz. All right, so that is to say that the infinitesimal change in f as you move dx, dy, dz away from 3, 4, 12, that is to say this point right here we should have thought as 3, 4, 12. The change in f df is this dot product. Okay, so we are meant to now estimate the change as we move some small distance in the direction of a particular vector. Now, I am supposed to look at the vector 3, 6, negative 2. So I'll be looking at 3, 4, 12. Let me take that 1 over 13 squared, put it on the outside, and I am going to dot with the vector 3, 6, negative 2. Okay, so this would give the change in f when we go from the point 3, 4, 12, and it just so happens 3, 4, 12 ended up there also. But this is the change as we go from 3, 4, 12 to 3 plus 3, 4 plus 6, 12 plus negative 2. No, that's not what I want. What it says is move a distance of 0.1 in the direction of that vector. Okay, so the direction of that vector is that vector divided by its magnitude. Its magnitude is the square root of 3 squared plus 6 squared plus 4 squared. So let's see. The magnitude of 6 squared is 36 plus another 4. That brings me to 40. And that with another 9 is 49. So square root of 49. Okay, so what I have right here is this, if I put a 1 up there, okay, this now is gradient of f evaluated at 3, 4, 12, dotted with a unit vector, and that's not what I want either. It says a distance 0.1 in the direction of that unit vector. So what I should do is multiply this unit vector by 0.1. There we go. And so now I'm taking the dot product of the gradient with this rather small vector. It was of length 1, and then I multiplied it by 0.1. So it's actually of length 0.1. I guess that's fairly small. That is the change in f as I go from 3, 4, 12 out to this point, which is 3 plus 0.3 over square root of 49, etc. Okay. So, wait a minute. 49, is that a perfect square? I think 7 squared is 49. Is that right? Okay. Assuming it's right. That's 7 down there. Okay. So I'll take this dot product. First of all, I'll take the 13s over here. 1 over 13 squared. They got that 0.1 upstairs from that. And downstairs, if the square root of 49 is 7, then I'll just put 7 right there. Now, that's not a 0.7. That's a times 7. They use dots for times sometimes. And then I've got this dot product, and that is 3 times 3, which is 9, plus 6 times 4, 12, 24. And then I've got negative 2 times 12. Hey, wait a minute, that's negative 24. I could simplify that. Okay, so that is the total change. I'm running out of paper, and I would like to do this on one sheet of paper, so I'll put right here 0.9 divided by 13 squared times 7. Now just think about that for a second. That's a fairly small quantity, 0.9, that's less than 1, divided by 13 squared. Whew, I'm getting much less than 1. So this is a fairly small change, which is about right, because this vector, this displacement vector that told me how far to go from 3, 4, 12 is actually fairly small. I don't expect f to change all that much. Okay. So I didn't get to verbalize that one very well. I would have liked to have said the change as you go from this place to this place was that, but maybe I'll get that in the future examples. And for this one, I'm just introducing you to the differential. So maybe I still did a good job. Thanks.